Okay, so our next topic is going to be rotations, and a rotation is just a transformation where it's rotated around a fixed point called a center of rotation at an angle that's given. Our center of rotation for this chapter will always be the origin, and unless we otherwise tell you, you can assume that all of the rotations are going to be counterclockwise. So remember, counterclockwise goes that way, like this, okay? And some rules for counterclockwise rotations is anytime you are given a point, x, y, there are certain rules. If you rotate 90 degrees, 180 degrees, or 270 degrees. So if you look at these rules here, you've got a point x, y. If you rotate 90 degrees, the rule is going to be you're going to switch the x and the y becomes the opposite sign. If you are rotating 180 degrees, you're basically going to just change the sign of both x and y. And if you are rotating 270 degrees, you're going to change x and y, the order of them, and then change the sign of x to the opposite of what it currently is. So let's look at a couple of examples of each of these. We'll do one example of 90, one example of 180, and one example of 270. So it says graph the triangle with the given vertices and its image after 180 degree rotation. So let's look over here to start with. What's the rule for 180 degrees? Well, if you go back to that previous slide, the rule is you are basically just going to change the sign of your x and your y. So if we look, let's plot our original ordered pairs. A is -2, 1. So there's going to be A. B is at 3. 1, 2, 3, 1, 2, 3, 4. There's B right there. And then C is at 2, 0. So there we have our triangle. Now we're going to rotate that triangle 180 degrees, which means we are rotating it counterclockwise. Okay, and our rule is going to be we are basically just changing the signs of x and y. So if we started out at -2, 1, we are going to, our a prime is going to be the opposite of -2, which is +2, and the opposite of 1, which is -1. 3, 4 is going to be -3, -4, and 2, 0 is going to be -2, and the opposite of 0 is still just 0. So if we go ahead and graph those new ordered pairs, 2, -1, there's going to be our A right down here. B is going to be at -3, -4, which will be right there, and then C is at -2, 0, right there. And if you notice, the size and shape of the triangle has not changed. It is just rotated halfway around, or 180 degrees. Okay, so our next one here, this time we're going to rotate 270 degrees. And our rule for 270 degrees is we flip-flop x and y. So we're going to have y and x. And the x becomes the opposite sign of what it currently is. So our rule for a 270 degree rotation is going to be y -x. So if we plot our original points, 3, 1, there's our S is at 5, 1, T is at 5, -3, and U is at 2, -1. And we just connect our dots, make a quadrilateral, and we are going to do a 270 degree rotation. So remember from what we talked about before, we start with blue and then we go to red. So I'm going to actually do that this time. So we are going to flip-flop our x and y. So 3, 1 is going to become 1, 3, and then that x value of 3 becomes the opposite sign. 5, 1 is going to become 5, 1, and then that 5 becomes the opposite sign. 5, -3 is going to be -3, 5, and that 5 becomes the opposite sign. 2, -1, we're going to flip-flop them, -1, 2, and that 2 becomes the opposite sign. So then if we go ahead and graph these, we're going to be at 1, -3. There's going to be r prime. 1, -5. There is S prime, -3, -5. There is T prime, and then U prime is -1, -2. That's going to be U prime, and if we connect our dots, we have the exact same shape. If I could draw a little bit straighter lines, the exact same shape, rotated 3/4 of the way around counterclockwise, so each point is rotated 270 degrees. If we have a 90-degree rotation, 90 degrees means that we are going to flip-flop our X and Y, so we're going to have Y and X, and our Y becomes the opposite sign. Okay, so let's graph our original triangle, JKL, 3, -1. K is at 4, 3, 1, 2, 3, 4, 1, 2, 3. And then L is 1, 2, 3, 4, 5, 6, 1, 2. Okay, and there's L. And if we go ahead and make our triangle, technically that should be in blue because remember our pre-image is always in blue, but I've already got it drawn in red, so we're just going to leave it how it is, and we'll just make the next one black. Sorry about that. So we're going to flip-flop our X and Y, so 3, -1, we're going to flip-flop them, and our Y value becomes the opposite sign. Well, the opposite of -1 is +1. And then 4, 3, we're going to flip-flop, and the opposite of 3 is -3. 6, 2, we're going to flip-flop, and then the opposite of 2 is -2. So then when we graph these, we're going to be at 1, 3. There's our J prime. K prime is at -3, 4. And then L prime is at -2, 6. If we connect our dots here, we have the same triangle, just rotated 90 degrees counterclockwise. And then the other thing that we can do with this is we can actually do compositions like we did before, where you do more than one transformation. So if we go ahead and just start by graphing triangle RST, we're going to be at 2, 3. So let's go 2, 3. So there is R. And then S is at -4, 1. And T is at 1, -2. And the first thing that we are going to do is we are going to reflect it in the y-axis. Okay, so we did the reflections on Friday or last week. Okay, so when we reflect across the y-axis, remember we are going across the vertical axis. So every point is going to go across that y-axis. So our first point R started out at 2, 3. It's 2 units to the right of the y-axis. Now it's going to be 2 units to the left of the y-axis. So our R prime is going to be -2, 3. S is currently, let's see, 1, 2, 3, 4 units to the left. So now we're going to go 1, 2, 3, 4 units to the right. And there's going to be our S prime. And then T is currently 1 unit to the right, so we are going to move 1 unit to the left. So now in red, we have reflected across the y-axis. So let's fill in our points here. S prime, well, it was at -4, 1, so now it is at +4, 1, because after we reflected it across, and then T is at -1, -2. Okay, now we are going to rotate 180 degrees. So let's go ahead and think about our rule. Our 180-degree rule is going to be opposite of X, opposite of Y. Okay, which means basically we're not going to flip-flop any of the order. We're just going to change the signs. So instead of -2, +3, we're going to be at +2. Change the color here because we're going to go to green because that's our next one. We're going to be at +2, -3, because that's our rule. We just flip-flop the signs, not the order. Then we'll be at -4, -1, and oops, 1, 2. So if we plot those points, we're at 2, -3. There's going to be our R double prime, -4, -1. There's going to be our S double prime, and T is at 1, 2. Oh, goodness, we're getting to be quite a little bit of mess in here. T double prime, and if we graph it in there, that is a little bit of a mess, but the green is the red one rotated 180 degrees. Okay, the next thing we're going to talk about is rotational symmetry. Rotational symmetry basically means if you put a pin smack dab in the middle of this shape, after how many degrees would it land on itself again? So if you look at a rectangle, okay, if you start rotating it, it has 180-degree rotational symmetry, because that means that it's going to rotate around 180 degrees and it will look exactly like it did before. Now, if we only rotated it 90 degrees, it would look like that. So if we had to go 180 degrees and then technically 360 degrees all the way back to the beginning would be the two, but we don't have to list 360. We only have to list those less than 360. Okay, if you look at the star, okay, if I put a pin in it here, right here in the middle, it's kind of like a pinwheel, and you started spinning it, think about how many times it would land on itself. Well, it would rotate this far when this point gets over to here, and it'd look exactly the same. And then we could rotate here, rotate another so many degrees. Well, how many degrees is each of those rotations? Well, to figure out how many degrees it is, we know that all the way around is 360, and it is making 1, 2, 3, 4, 5 stops along the way. So if we divide 360 divided by 5, we get 72. So it will have rotational symmetry at 72, 144, and then we could continue to add 72 until we get to 360 degrees. So a parallelogram, if we put a pin in the middle, okay, well, if we rotate it 90 degrees, it's not going to look the same. If we rotate it 180 degrees, is it going to look the same? So if we rotate a parallelogram 180 degrees, it maps itself onto itself. An octagon, we think about 1, 2, 3, 4, 5, 6, 7, 8 times it's going to map itself onto or rotate onto itself, which means we need to take 360 and divide it by 8, which means every 45 degrees it has rotational symmetry. So at 45, 90, 135 degrees, 180 degrees, and then we could keep listing all the way up to 360. If you look at the trapezoid, if you put a pin in it, rotating it 180 degrees is not going to be helpful. You'd have to go all the way around to 360 to get back onto itself, so that actually has no rotational symmetry. All right, if you want to go ahead and pause the video, stop the video, and just try these last couple by yourself, that's fine. I'm going to actually put the answers in here, but if you want to stop it, go ahead and pause it, try them, and then just check back. So the rhombus is what that is. It looks a little bit like a diamond. If you put a pin in the middle at 180 degrees, it would rotate back onto itself, so 180 degrees. If you look here at 1, 2, 3, 4 times, it will map onto itself, so 360 divided by 4 is every 90 degrees, so you'd have 90, 180, 270, and 360. And then if you look at that triangle over there, there's no way. The only time it's going to map back onto itself is if you go all the way around, so that one would have no rotational symmetry. Okay, good luck, and I hope that was helpful in helping you understand rotations and rotational symmetry.